For part 2 of our video, we're going to be working with something called electron configurations. And electron configurations, another way to think about it is, what is the specific electron's address on the periodic table? So, like we said before, the periodic table is arranged in such a way that it gives us a lot of information. So this specific information that we're going to be looking at today is how can we identify the location of one specific electron on the table? And we have to label this table in a way that helps us determine the address. So this is where you're going to need some crayons or colored pencils or markers or something to identify the different areas of the table. Now, the first thing we want to look at is what's called the S block. So the periodic table is divided into a series of what we call blocks or areas. The first one, the S block, contains group number 1 and group number 2, the entire column, and in addition to that, helium. So everything in those first 2 columns are the S block. The next thing we want to highlight are what's known as the P block. And the P block is this 6 by 6 block of elements on the right. So boron over to neon, and then everything down below that through row number 7. That's the P block. And you can pause this video along the way to give yourself a minute to color in these different areas. After the P block comes the D block, and the D block are what we would refer to as the transition elements in the middle. So from scandium down to actinium and then over to zinc. So that 10 by 4 block in the middle of the periodic table. And then the last block is the only area that's left. That's the F block. The F block is the 14 by 2 block down at the very bottom of the table. The first element that we want to look at is hydrogen. Remember, hydrogen is right here. So let's look at hydrogen's electron configuration, and then we can dissect it a little bit to talk about what each of the numbers mean. So hydrogen's electron configuration is 1s1. So we say this like 1s1. The first one refers to the row. Now we'll find that later on this pattern kind of breaks a little bit, but at least in the beginning, we're referring to that number in front, or the coefficient, as loosely being correlated to the row number. So you can see those row numbers right here. The letter in the middle, S, refers to the block. So we've already labeled this area here as the S block. The one up at the top refers to which electron is it in the block. So notice in the S block, we can either be electron 1 or we can be electron 2. In this case, we're looking at hydrogen, and it's electron number 1. So again, this is referring to electron number within that block. So what this is telling us is that we are the first electron in the S block of the first row, 1s1. Looking at helium, remember, helium is on the right side of the table because it has the same chemical properties as the noble gases, but it's still considered to be in the first row and the first 2 electrons of the first row, which is why it's still in the S block. So helium's electron configuration is 1 because that's the row number, so it's in row 1. It's in the S block, so we have the S. This time it is the second electron, so 1s2. We have to put a 2 there because we're still counting that hydrogen is there. Hydrogen is considered part of helium's electron configuration. Now at this point, we've reached the end of the S block, so we need to move to a new row. So in that new row, remember, we go in order of increasing atomic number, so we have lithium next. We have to say where we've been. So we first have to say where we've been, and now we can say where we're at. So where we've been is 1s2. We have filled up 1s2. Remember, when we take an electron, we can't just plop it in the middle of an atom. We have to build up from the inside out. So we have to fill those inner shells before we can move to the outer shells. So 1s2 shows me that I've already filled up that inner shell. And now I'm moving to the next shell out. And lithium is in row 2. It's in the s block, and it's the first of 2 electrons. So the entire configuration for lithium is 1s2, 2s1. Moving to beryllium, we have to show where we've been. We've filled up the 1s orbital, so that's 1s2. It's in row 2, it's in the s block, and it is the second electron of the s block. So the first term shows us where we've been. The second term, or the last term of an electron configuration, shows us where we are. So beryllium's electron configuration is 1s2, 2s2. Now again, moving over in order of atomic number, and when looking at boron, we have to show where we've been. So where we've been is 1s2, 2s2, still in row 2, because we are now right here, 2p, we are now in the p block, 2p1. So everything we filled up to this point is 1s2, 2s2. Where we are now is 2p1. Again, we can't just say 2p1 because we're not just showing the electron that's been plopped right in the center. We are showing the entire configuration, where we were or what we had to get through to get to where we are now. So again, for boron, 1s2, 2s2, 2p1. For carbon, at this point, we can look back at boron's electron configuration, and what we should notice here is that the p block in each of these rows, or each of these energy levels, can accommodate a total of 6 electrons. So what that means is every time we move over 1, or in other words, every time we add another electron, all we're doing is changing this number. So we can change that number until we reach the maximum, until we get to 2p6. So then carbon still goes through 1s2. This was 1s1, 1s2. Still goes through 2s2. And now we are right here. So we're at not 2p1, but 2p2. And we're going to keep adding 1 within the p block of the second row. So the next one, nitrogen, would be 1s2, 2s2, 2p3. The third one over in the p block of the second row. Oxygen, 1s2, 2s2, 2p4. We're in the second row, or second energy level. We're in the p block, and we're the fourth one over. So again, this is 1, 2, 3, 4, 5, 6. The neat thing about this is you can also add up the total number of electrons. And remember, since each of these represents 1 electron, if we add up all of the exponents, that tells us how many electrons that element should have. So we know that oxygen has 8 protons, therefore also has to have 8 electrons. And we know that 4 plus 2 plus 2 equals 8. So if we have the right electron configuration, these exponents, or these numbers, should add up to the atomic number of the element. Next is fluorine. Fluorine is 1s2 to show those, 2s2 to show those, and now we are 2, we're in the second row, we're in the p subshell, and we're at 3, 4, 5, 2p5. This is pretty neat because once you start seeing the pattern here, it's pretty easy to read. And you'll notice this term is the last term that shows you where you're at. So if I'm giving you an electron configuration and you don't know that this is element fluorine, and I said identify the element based on its electron configuration, you can look at the very last term in the electron configuration and you can tell me that 2p5 means I'm right here and the element is fluorine. So you can look, going the opposite direction, you can just look at the electron configuration, the very last term, and that alone, in most cases, will identify the element. Neon. We're now at the very end of the P block. So our last term, you can probably tell me what the last term is without going through the rest of it. We're in the second row, we're in the P block, and we're the sixth electron. So therefore your last term is 2p6. We've reached the end of the row. So now we're starting here with sodium. We've reached a new row, so we're not in 2 anymore, we're in 3 now. We still have to show everywhere we've come through to get to the point that we're at right now. So we're at 1s2, 2s2, 2p6 is now filled up because we have gone all the way through neon. And now we're starting a new row. So again, this is where we were. That's what's already filled up. The last term is just what's available in the outer shell. So this means 3, we're in row 3, we're in the S block, and we're the first electron of the S block. Look at this electron configuration. If you look at the very last term, you should be able to identify what element that is just based on its last term, at least for the main group elements. Magnesium is next. 1s2, 2s2, 2p6, 3s, and now we are the second element of the S block in the third row, 3s2. Now there's something called noble gas notation. So with noble gas notation, what I can do is look at the very last noble gas that we were able to identify. In this case, it's neon. So if I'm writing noble gas notation, this is just a way to shorten up my electron configuration just a little bit. I can look at the part of my electron configuration that represents the noble gas, and we know that's everything up to 2p6. And instead of writing this entire electron configuration out, what I can do is put the noble gas in brackets and only the last term. So it would be Ne in brackets and 3s2. Again, it only makes sense to do this for things pretty much after neon because anytime before that, you're almost writing out exactly the same thing anyway. So it's not really saving you any time. But anything after neon, it makes sense to use noble gas notation. For aluminum, we have 1s2, 2s2, so this was 1s2, 2s2, 2p6, 3s2, and we stop right here. So our last term is 3p1. Again, we've reached a P block. So at this point, what I can do is now just change this number only, because remember that number can go all the way up to 6. So as I move across the periodic table, all I'm doing is adding one more to that number. So silicon is now 1s2, 2s2, 2p6, 3s2, 3p2. Continuing on, phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. And I'm just going to add one more each time. For sulfur, 1s2, 2s2, 2p6, 3s2, 3p3. 4. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. And then for argon, going through the same process we've already seen. 1s2, 2s2, 2p6, 3s2, and then since we're at the end of the p block in the third row, our final term here is 3p6. We're going to skip ahead to scandium because what we see happening with scandium is just a little bit different, or rather things start to take a little bit of a turn in terms of energy levels once we hit this D block area. So what we noticed with the S block was that S started at energy level 1. What we noticed with the P block, there was no 1p. It started at 2p. So we noticed that the P block started at energy level 2. So in following with our pattern, because everything in the periodic table is set up in terms of a pattern, the D block starts at energy level 3. Now I know this looks a little bit weird, but we'll take a look at it in a minute where we can see exactly how these energy levels are arranged. So remember, the way the periodic table is set up is in order of increasing energy levels. So this tells us that the 4s energy level, which is right here, is slightly lower in energy than 3D. And we'll talk a little bit later, maybe chapter 11, about why that is the way that it is. But right here, we're just learning a pattern. So for scandium, we still are going through everything we've already been through. So we can say we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and our last term, this is where it's a little bit different, is 3d1. So we have to start in the lowest energy level of that subshell. So that means we have to start at 3d. Now, the nice thing about this is once we get to that 3d level, we can see that we go 10 electrons over. So all we have to do, like we did with the P block, is to change this one at a time until we reach the end of this row. So if I had zinc, zinc would be then 3d10. So the next one we want to look at is gallium. And we're looking at gallium because we want to see what happens as we come out of this 3D subshell. So notice gallium being right here is right after 3D. So we want to see what happens when we're done with 3D and we need to start over again. So we have the same thing we saw before, and we just said with zinc, we would end on 3D10. So notice we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now what comes next? Notice the S block and the P block are still in that group that we refer to as main group elements. So these follow the same numbers that we would see over here. So this means that when we get back over to the P block, remember we started at 2 and this was 3. So next this would be 4. So we see that we just put 3d10, and our very next term would be what we see here. It would be 4, because this is the fourth row of the P block. How many electrons over is it? It's 1 electron. So gallium's electron configuration would end at 4p1. If we wanted to turn this into a noble gas notation, because we can see that it's already getting pretty long, we want to end with our last noble gas, and that was at argon. Argon filled up the 3p subshell, so argon ended right there. So if we wanted to, And if you had permission to shorten this up in noble gas notation, you could say argon in parentheses 4s2 3d10 4p1. Now, what we're going to look at is how this works in terms of actual electron filling. So it's easy to look at this on paper, and it's easy just to be able to recognize the pattern from the periodic table. But what we want to do here is talk about how this information is useful and where we can see this information be applied. So looking at the electron configuration, 1s2, 2s2, 2p6, 3s1, we can maybe identify this element first. So what we want to look at is the very last term of the electron configuration. And this last term, 3s1, means we're right here. So we're talking about sodium. We're talking about sodium because this is an easy example that we can use at home. If you've ever boiled a pot of water, say you're making pasta, and you're boiling water, and maybe you put salt in the water before or as it's boiling. Now, if you put salt in the water and you have a gas stove, remember gas stoves, you can see the blue flame coming up from the burner. So what happens sometimes is you spill a little salt outside of that burner. And if you do that, you notice that the color has changed of that flame. It was blue. When you put salt in that flame, it changes to an orange color. We're going to do a lab involving this, so you'll be able to see through one of our pivot activities how different metal cations give off different colors, or different metal elements give off different colors. But what we want to investigate here is why that happens. So what we can see is, this is called an orbital diagram. So this shows us all of the different subshells from the lowest energy level, which would be 1s, all the way up to the highest, in this case 3d. That's all I had room for on this page. So we want to show how electrons are added to an orbital diagram like this, starting from the bottom up. So that's what's known as Aufbau. Aufbau is the German word for build up. So the Aufbau principle tells us that we start at the bottom and we work our way up. And we know this in reading the periodic table because we know we have to fill the bottom energy levels before we work our way up. So the first term, 1s2, means there are going to be 2 electrons in the 1s subshell. So I'm going to show that one goes up and the other one goes down. And there's another principle in electron filling that tells us they have to have opposite spins. And that's why we show one arrow up and one arrow down, to just let us know that they have to spin in opposite directions to be more stable. Once I filled up the 1s orbital, I can move on to 2s. And I'm going to do the same thing. After we've done 2s, we can move on to 2p. Notice here, we have 2p6. Now the p orbitals are special because I can't just put one up and one down in each orbital. What we need to know here is that we have to maximize unpaired electrons first. So we can see that we have to put one in each one in the same direction in each of the 2p subshells before we can now move up to the next one, or come in and put the one in the downward facing direction paired with the ones that were already there. So this would be 2p3. We can now come back and we can put another electron going in the downward facing direction. So this fills up our 2p6. We don't really have time to get more into it than this. There's a lot more involved here, but for now we're just using a simple version and not complicating it too much for our purposes while distance learning. The next part is the last term, and that's 3s1. So we're showing one electron in the 3s orbital. So back to our flame and salt example. So we know that this is a 3s1, and we're talking about sodium, which means if we have energy that is getting put into this sodium sample, then what's going to happen? And this is in terms of the flame. So if I have a sodium atom And just in the outer shell, we have one electron in that sodium atom, and I add a flame. Bunsen burner with a flame underneath, or the flame of my gas stove. What's going to happen is I'm going to be giving this electron, in adding flame to it, I'm going to be giving this electron just enough energy to now promote itself. So it's going to move up an energy level. And when it does that, it's holding on to this energy that it's absorbed. But what has to happen now is it has to fall back down at some point. It's not stable unless it's in that position where it's in what we call the ground state. As soon as I give it some energy, it's been promoted to what we call an excited state. So it's only stable for so long in the excited state before it then has to expel that energy. And when it expels that energy, that electron falls back down. The energy that's expelled is what's called a photon. And you may have heard this before. A photon is what's known as a packet of light. So depending on how far that electron falls back down, it's going to be giving off light in a particular wavelength. And every wavelength is a different color. Sodium, for example, falls down at a particular wavelength that it gives off an orange light. So that's what we're going to be investigating when we look at the flame test lab that we're going to be looking at. This is also responsible for what you'd see in fireworks. Fireworks are made of things like lithium and potassium and sodium, metal elements that when they have an electron promoted to an excited state will fall back down, releasing a photon, which is a packet of light, and that packet of light has a certain amount of energy tied to it, and the amount of energy released shows us a color. That color is what we see when we look at salt falling on a stove or fireworks as they explode in the air.